Good day everyone. In this video we will talk about probability, and of course we are going to do so using R. To understand what probability is, let's have a look on flipping a coin event. So let's flip a coin using R. How are we going to flip a coin using R? We will create a coin, which here will be a variable composed of a character vector containing head and tail. So now we have a coin and we want to flip this coin. To flip the coin we have two options. First option is we are flipping a fair coin. Second option is we are flipping an unfair coin. And flipping a fair coin, that means that I am going to take a sample from this character vector, and the sample will be, we will flip the coin one time, so we'll put the size equals 1. We will flip the coin one time, and because it is a fair coin, the probability of landing on head or tail will be 50-50, which is 0.5. And we will put replace equals true. Since we are drawing only one size, replace equal true here has no significance because it will only draw one sample, one time. And let's flip the coin, and now let's have a look on the results of the fair coin. So now it is tail. So let's flip the fair coin again. Let's flip our coin, which is a fair coin, once again. You go on this line again and click run, and it's a tail again. It's a tail again. Now it's a head. It's a tail. Are we sure that this is a fair coin or what? Okay, head. Okay, and tail. So I suspected that this coin might be unfair, but it turned out it's some sort of a fair coin. We can flip it 10 times together and in sequence, and with replacement equals true. Let's create another variable called fair coin 10, and let's run it, and we can see the distribution. So 4 heads and 6 tails, and we can plot it using bar plot function, and we can see 6 tails and 4 heads. Let's repeat it again. Okay, more tails, now more heads. Okay, let's repeat the flipping 100 times. Okay, let's repeat it 1000 times. Okay, have you noticed anything? Have you noticed that when we increase the number of repetition of coin flips, it eventually approaches the ideal value, which is 50-50? Let's make it 1 million times. Okay, and by the way, if you see this here, you can eliminate this format and display normal numbers by using options. Options and sci-pen equals, you can put 3 nines and rerun everything again, and you will see that numbers are displayed in a normal way. If you table the fair coin, we can see that is almost approaching 500,000. So whenever we repeat, we increase the number of flips, it approaches the ideal distribution as we see. And this is a very important notice. Now let's see what happens if I replace this fair coin with an unfair one. Let's make it 30% heads and 70% tails, and let's run 1 million times. And you can see that when you approached when you repeated 1 million times, you approached the ideal value. Let's suppose we have a die, and this die has 1, 2, 3, 4, 5, 6. And let's say it's a fair die, and we wanted to sample from fair die. Let's put the arguments in a very accurate way. X will be the fair die, and size, let's start with 1, and probability, let's start with a fair die, so it will be 1/6 repeated 6 times. And replace equals true. So I think we are good to go. It's die, not fair die. Okay. Now let's see the results. Okay, it's 4. Try again. It's 1. Try again, and so on. So now we can do it 100,000 times, and table the results. And we can see it is almost the same, so approaching the ideal proportions. And we can bar plot it. And you can see it is the same. If we reduce the number of die rolls, we can see clearly that it does not approach the ideal values. Okay, dear friends, now let's work on a dataset, and we are going to learn about what's called bootstrapping. Bootstrapping means that you take sample from your sample, in other words, resample your sample, and it is based on what is called the bootstrap principle. And the bootstrap principle states that sampling with replacement behaves on the sample the way the sample behaves on a population. So through bootstrapping, you are simply taking samples over and over again from the same group of data or from your sample data to estimate how accurate your estimate is about the entire population. If you take one sample only and make estimates of the population, you might not be able to estimate how accurate your estimate is. With bootstrapping, you use the original samples that you have in hand to generate multiple samples. The new samples or the resampled samples are not identical to the original sample. So there are variations in the means and estimates of the samples, the new samples, and then you will be able to see how accurate your sample is. Of course, you always have the option, instead of bootstrapping, to take several new samples from the population, but sometimes this is not feasible. So if taking multiple samples from the population is not feasible, one solution is to make bootstrapping. When we go through the next lines of code, and as I promised you in the first lecture, that while we go forward through this course, you will learn about new terminology and new functions every lecture.